This is me on top of a speeding train, and this is me in a hot air balloon to answer some of the most debated science questions on the internet. For example, my hot air balloon pilot here says he can land me anywhere I want, and yet there's nothing here that resembles a steering wheel, which begs the question, how do you actually steer these things?
So we steer.
And now I'm on top of the train to learn once and for all, why do you land in the same spot if you jump inside the train, but not if you jump on top of the train? But I'm not stopping there. Because today we're going to investigate 5 more physics and engineering puzzles using simple demonstrations as we go. Because our goal by the end of this video is not for you just to know the right answers, but more importantly for you to understand why they're the right answers. To kick things off, I've got a science riddle for you that most people get wrong. What is the first man-made object to break the sound barrier? In other words, an object that travels more than 767 miles per hour through the air, exceeding the speed of sound, thereby creating a super loud sonic boom. So what do you think? Most people I ask say either a bullet or a rocket or even a jet plane. But this tech goes way back, like 5,000 years way back. Because the first man-made object to break the speed of sound is a whip. The sound you just heard was literally a sonic boom, which means at the peak of its motion, the tip of the whip is moving faster than 767 miles per hour. Okay, so if you got that right, time for a bonus question. What's almost surely the first time you yourself heard a sonic boom? Here's your clue. It's a near statistical certainty that everyone has the same answer for this going back millions of years. That's right, thunder. Basically, the lightning superheats the air 5 times hotter than the surface of the sun, and this causes the air to expand so rapidly, it breaks the sound barrier once again, creating a sonic boom. And if that juicy nugget of knowledge just made your brain feel really good, ow! Make that sound cooler in post. Yeah. Buckle up, because we've got 6 more to go, including, at number 2, have you ever noticed when grabbing drinks from a cooler that even though they have the same amount of liquid inside, regular Coke sinks, yet Diet Coke floats? Now, why would that be? Well, our first clue is that we know less dense objects like this cork float, and more dense objects like this bolt sink. However, that's not only true about different objects, it's true about different liquids too. Like for salad dressing, how the less dense oil floats on the more dense vinegar. And sure enough, when we compare the respective labels, you'll notice one glaring difference. Regular Coke has more than 3 tablespoons of real sugar, which makes this can more dense than the Diet Coke, which just has artificial sweetener. That means this one's just a little less dense than water, causing it to float, while this one's just a little more dense than water, causing it to sink. But we can take this to the next level. Here I have a wall that I filled with 8 different household liquids, from honey, dish soap, to baby oil. And they naturally stack themselves with increasing density as you go down. So if we dump, let's say, a bunch of golf balls in, they'll sink like a Coke can through all the layers until they hit a layer that's more dense than they are, at which point the golf balls stop falling and come to rest on top of that layer. Are you kidding me? Which means you can have a different item come to rest on every layer. Whoa! As long as you spend way more time than you care to admit. Cool. Testing way more items than you care to admit. This one's a dice roll. But in the end, it's not hard to rationalize the wasted time when it looks this cool. By the way, you can make a simple version of this yourself at home by filling a drinking glass with baby oil and colored water, and then plopping in a Lego guy to ride the ocean waves. So this obviously works with household liquids, but what if the liquid was metal, like this? Because this bowl has 24 pounds of mercury. It's hard to even submerge my hand in here. Which means if I take an actual cast iron anvil, it should float like a Diet Coke. Let's test it out. Look at that. I mean, I understand the science behind this, but it still breaks your brain. This is actual cast iron. It's heavy, and yet when you put it in mercury, it bobs like a cork. Let's go bobbing for anvils. For number 3, a while back I read about a famous mathematician for the 1600s who noticed that when he would hang up multiple pendulum clocks in his house, they'd eventually sync up their swings, and then they'd just stay that way. So he wondered, just like I did when I first read this, how are these purely mechanical clocks that weren't touching somehow communicating with each other, and after a period of time, agreeing to swing in perfect unison. And since the unofficial motto of Crunch Labs is think like an engineer, I decided to create an experiment to test this for myself. So we got 4 clocks and put them on the wall, and after 4 days, nothing happened. But when you're thinking like an engineer, you know that's not a failure, that's a clue. So I reread the story and picked up on an important detail I'd missed the first time. The clocks weren't mounted on a wall in the way we think of today. It said they were mounted on the same wooden beam that made up part of the wall. And given the construction methods of the 1600s, there's a good chance that board had a little wiggle to it. And that wiggle is a very important detail. Here's what I mean. If I swing this sledgehammer pendulum below me while standing on firm ground, then it's just the sledgehammer pendulum that you see moving. But if I stand on a skateboard where I don't have firm footing, now you can see the pendulum is in fact pushing back and moving me too. Now here's the wild part. Because the clock is securely attached to the beam, that beam acts just a tiny bit like the skateboard. So those swinging pendulums are ever so slightly actually moving the wall. So that means as the clocks are just slightly pushing back and nudging the beam, they start to influence and nudge each other too. So if there's a clock that's greatly out of sync with the others, over time those little nudges get it to line up. So after discovering all this, we took those 4 clocks and this time attached them all to a beam, which was attached to the wall with a little bit of wiggle built in. And this time after 4 days, nothing happened, which once again was a clue, not a failure. Because it turns out for this to actually work with pendulum clocks, you need a very precise ratio of clock to pendulum mass, like this setup here. So while I couldn't get my hands on the perfect pendulum clock, here's another way to observe the same phenomenon with 140 pendulums all sitting on a board that can freely wiggle back and forth. All right, let's give it a shot. Little help here. This is truly one of the coolest things I've ever seen. It's like a bunch of stormtroopers. And just to give you a sense of how quickly they sync up, here's an uninterrupted take so you can see for yourself as the chaos turns to order in less than a minute. So as you can see, even though we started them totally random, in less than a minute, those nudges do in fact influence each other till they're all swinging together, just like the clocks 400 years ago in the mathematician's house. Coming in at number 4, have you ever noticed every time you see a full moon, it always looks the same? In other words, it's the same side, even in pictures. Well, what about the other side? Well, it turns out we don't see the other side because the moon is rotating perfectly in sync with its orbit around the Earth. So we only ever see the googly eyes. But that's wild. Like, what are the chances that those would sync up perfectly? Well, we call this tidal locking. While it seems unlikely, you see this with pretty much all the other planets and their moons in our solar system too. And this simple demo will give us the right mental model. Now, if the moon was perfectly spherical and balanced, it would spin like this, and one side wouldn't be more likely to line up with Earth than the other. But the moon's not perfectly spherical. Over time, that constant pull of Earth's gravity has caused it to be sort of slightly oblong, which we've sort of exaggerated a little bit here, but now you'll see, since the center of gravity of our moon doesn't exactly line up with the axis by which it rotates, like it was here, now, no matter how I spin it, it always happens to be that the heavy side of the moon always